Hi, this is Koiro with a slight upgrade on the Leningrad project. The last video I published, number 4 in line, we made some progress and we was actually able to run the test diagnosis program, although it was almost impossible to see it because the screen was so garbled. So what I've done to make a better test of this, I have tested some of the ICs, and as I told you last time, we had to look into the video decoder circuit. And as a matter of fact, I found that the 74LS165 chip that was standing as the shift register on the last part of the decoding, that was actually defect. And I will show you later how I tested that. And also I've been changing around a bit on the DRAM chips to check, and we are going to see some strange behavior there. But as you remember last time, I thought that there was some frequency drift in the oscillator circuit, and to get rid of that, I told that it was best to get a finished metal can oscillator to put into the circuit. But I have ordered those chips, but they have not arrived yet, so I actually made a shortcut. My trusty old Unity UTG 2025 function generator cannot output more than 5 MHz in square wave pulses. But as I was talking about last time, the oscillators almost always does not produce a perfect square. So what I'm doing here is actually that I have lifted the pin 6 out of the socket, and I'm injecting 15.315 MHz sine wave into this pin. And this I do with a slight overdrive. So this chip is actually producing squares on pin 7 on this chip. And this is the 74LS04 that was doing the buffering for the oscillator already. So this is the output of the oscillator, and I just lifted this pin and steer the frequency straight into the buffer. And I was not really surprised when I saw that the screen cleared up, and we are going to look into that in a second. I've also replaced the CPU with the one that was originally in the circuit. As I said last time, it really is no fault with this CPU. I was only testing around a bit to see if the old C-Log Z80s I have was okay. And I still have the test ROM or the diag ROM chips in here. So the changes from last time is that I've changed this chip, the 74LS165, and I inject the clock stripe in here from the function generator. Here we can see the signal that's fed into the 74LS04 gate, and this is the signal that's coming out of the 74LS04 gate. And as you can see, it's not a perfect square, but it's actually not worse than the one that came out of the oscillator, and as you can see, the frequency looks more stable. And this is the signal out from the 74LS074 that acts as a frequency divider and stands after the oscillator. And this is the clock signal that feeds into the Z80 CPU. So the signal is actually looking much better than it did with the original oscillator. The original oscillator is still spinning in here, and that might be a fault from my part, because I might be able to get rid of some noise if I turn it off. But this is actually the signal from the original oscillator, and as you can see, you have this shadowing next to the pulse that we take as a sign of frequency drift on the oscillator. As I promised you earlier, I will give you a short look into how I tested the logic gates on this board. It's actually possible to test every 74 kind of logic by doing the truth table method, where you take and make a table for the inputs, and you have the outputs that's supposed to be present when you make the changes on the inputs. And every kind of TTL chip works after this logic. You have some problems testing some of the buffers, some of the 3-state outputs, and some of the totem pole outputs and stuff. You have to do additional electronic to test, but otherwise it's just a simple test to see what you put on the input and see what the output produces. And that is the kind of test that the XG Pro programmer actually does. In the software here, you actually have an auto-find feature for detecting logic gates which you want to test, and this test is, in my experience, very accurate. And you also have the option to choose your device in this gate, and that you need to do when you have the gates that's almost the same. They just have inverted outputs or inputs, so it's not possible for the programmer to see if there actually is a fault with the chip. And here you can see this is the truth table for this device, and this is what you're supposed to get on the output when you are supplying this input. And here you can see that it actually failed one test, and that means that there are some internal fault on this gate. And when I tested 74 LS165 gate that I had in my spare parts storage, it tested okay. So the test is able to accurately decide if a 74 LS165 is okay or not. So I replaced this chip, and the next result you see on the video is actually the screenshots from when we run the test on the Leningrad board after we changed this chip and after we supplied the oscillator with the sine wave that was described earlier here. Yeah, for those of you who followed along on the test runs I had completed just now, you might notice that each test run produced a different result, and that means that this thing is not entirely stable, to put it that way. We have some common factors between all the errors we have encountered, and that is that IC6 low RAM is mentioned in all the tests, and the IC6 low RAM is the 0-bit of the video memory if we take this into the memory map. And the IC6, as we can see here in the schematics, is the 4116 memory chips. That was the low memory of the ZX Spectrum and the original memory in the 16K ZX Spectrum. And if I remember the memory map correctly, the 4K that's lowest in this memory decoding scheme is the video memory. And the Leningrad handles the memory quite differently, because there is only one memory bank in the Leningrad, and that consists of this 4164 memory chip. So the differences between the two designs could account for some of the errors that we see here, because we don't know exactly how the test and diagrams is handling the test regarding to memory. So some of the differences between how the memory decoding and the memory timings and how the memory reads and writes to the screen and to the other parts of the computer can be an issue here. But what we must consider is that every one of these tests produced different results, and that needs to be addressed. Because if there was some error just in the memory scheme, we should get the same result each time. And as I stated earlier in the DRAM Uno video, I have actually tested this memory chip for the Leningrad in a Commodore 64, and they actually run just fine. But I have one issue with that, and that is one of the memory chips, and that is the chip that stands in IC6 now. It's actually producing inconsistent results, and that means that this chip is producing the same error. So this is bit 0 in this configuration, but I can move this error to bit 1 by changing socket for this chip. And that means that even though this memory is working, the Leningrad might have the components running just slightly within their margins of operation, and we actually have seen some issues with noise and pulses on the line earlier. And before I do any more work on the Leningrad, I will put decoupling capacitors on every power line across each of the sockets on this board. So that means I have to get some capacitors and get them soldered onto the board, and this is a change I will do regardless of all the other components that I'm waiting for to address the other issues that we have experienced with the Leningrad. So that's it for this episode. Thanks for watching, and please hit subscribe if you want to be notified when I post another video. See you next time.